Hello everyone. In this lecture, we will learn how insert operation works in replactory. As an overview, we will learn the content of the given topics mentioned below as initialization of replactory, insertion cases in replactory, such as if z is root, root is black. If z's uncle is red, we recolor. If z's uncle is black and triangle formation, rotates z's parent. And finally, if z's uncle is black and we have line formation, we rotate z's grandparent and recolor. At the initialization part, we have node class which is used to create nodes for our replactory. Unlike in other binary search trees, node class holds additional variable of color where 0 means black and 1 means red. Red-black tree class has two instance variables such as root and tnull. Tnull is used to create null black nodes in our replac tree and takes constructor-defined values at the start of our program call. So whenever we need to set a specific node to null, we can basically make it equal to tnull. This becomes handy, especially for determining the black leaves and assigning a specific node to become a black leaf when needed. This said, at the next slide, we will dive into practical example and see how insert operation works in replactory. As our first key value, let's insert value of 50. So we create a new node and initialize parent, key, left and right pointers and color for it. Here, if you are wondering why new insertions are initialized with color of red at line number 8, I have explained it in the previous lecture where we talk about the definition of replactory. So before you move into this practical lecture, I highly recommend you to finish the previous lecture first. So as we continue on with this lecture now, at the next step we create yNull node at line number 10, which later on will be used to store and update the parent node of the inserted node. At the next code line, we define node x and initialize it to our root node. X node here is created to locate our new insertion using a while loop in our replactory. At line number 13, we check if x is not equal to tnull. If you look at slide number 3 at the initialization part, we set our root to tnull in our constructor. So this means at the start of our program, root will be equal to tnull. However, later on, we will modify our root node as it will be equal to our very first node with a key value of 50. So here now, we skip the while loop and set our new node's parent to y. So if a node doesn't have a parent, we know that 50 is the first insertion in our replactory and it will be our root node at the next line. From line number 25 to 30 we skip because we have executed the if statement at line number 23. At the next if check at line number 31, we here basically be sure that our actual node's parent is null, then change the color of our root node and return from our function. Next, we insert key value of 39. Again, we initialize its node constructor variables. We create a local yNull node, which later will be used to point the parent node of node 39. And we create local x node variable to find its location starting from root. This time x is not equal to tnull, so we go through the while loop and make y to be equal to x, where later on node.parent will be equal to y at line number 22. So next, same if check as in every binary search tree implementation to determine whether the inserted node will be located at the left or at the right subtree. At the next iteration, x will be equal to tnull because root.left was equal to tnull, so we skip the while loop and get to line number 22. In line number 22, we update the new inserted node's parent to point at y. And next, we do the actual insertion by using the y variable's left or right pointer. In this case, we know that 39 will be inserted at the left subtree, so line number 25 will be executed. Next, we check the parent node no longer null, so we check if the inserted node is the second node after the root. Yes, it is the second node, so we return from our insert operation, avoiding further executions. At the next insertion call, let's insert key value of 35. Here, I will leave the execution to slide animation as we are now familiar with the flow of our insertion logic. I will continue explanation when the execution reaches the balancing method. At the balancing method, we will see how our rep black tree will be balanced with the defined scenarios mentioned at the lecture definition of rep black tree. At line number 2, we simply define our uncle node. In the while loop, we create our logic and comfort the condition where if parent node is red, then its children are black, and iterate through the loop until the condition state is false. At the next line, with an if statement, we determine whether the balancing is applied at the left subtree or at the right subtree of our rep black tree. In our case, balancing will be applied at the left subtree. So we skip and get to else statement, which comforts the situation we have now. So as you know from the previous lecture, uncle node is equal to grandparents node's right or left pointer node depending on the subtree that we need to apply balancing. In this case, it is grandparents' right pointer since we are applying balancing to the left subtree of our rep black tree. And next, we basically check with which scenario we are dealing with. If you remember from previous lecture again, if Z's uncle is red, the only thing we do is recolor. But in our case here, it is T-null, and if you remember, T-null color is defined as 0, which means black from the constructor that we have initialized at the initialization part of this lecture. So this is why we will be skipping if statement here since we have a black uncle. At next, we check the other remaining conditions. At the next if statement, we can determine whether we have triangle formation in our rep black tree. If we had triangle formation or scenario number 3 at this current situation, we know that Z would be equal to parent of Z's right. Take a moment and just imagine that Z node is at the right subtree of node 39. Then you would see that we would be satisfying this condition and balancing our rep black tree by relying on scenario number 3. But it is not the case here. So we basically execute the remaining scenario where we have linear formation, which also means we have scenario number 4. In scenario number 4, we rotate Z's grandparent and recolor. For the sake of convenience, I recolored first, but you can go on and recolor after rotation with correct logic. This approach wouldn't break our rep black tree definition, and we would still have valid rep black tree after the recolored nodes. So next, let's go on and see how right rotation works in rep black tree with a node input. At the rotation method, we define a y node which we point to the left of the x node. Y node here again used to update the parent node of the rotated node. We point x's left pointer to y's right pointer, where in the end it will point to T-null. At the next if statement, we check if we have a value at the right pointer of node y. And if we did, then it would be parent of x. So it isn't, and we get to the next line after we skip the if statement. We change the parent node of y because now its parent will be pointing to x's parent. At the next if statement, we check whether the x's parent is null, because if it is null, y simply will be our new root. And yes, this is the case, so we change our root to get the same address as our y variable. X becomes as y's right pointer, and x's new parent is now y. After executing right rotation, we simply check if z is root, which comforts this first scenario. It isn't, so we again get the while loop head. Next iteration will not be executed because z's parent is now black node. So we skip the while loop and be sure that our root is black at the end of the balancing. So at the previous insert, we have seen scenario number 4. Now we have 3 more scenarios remain to testify. In this insert, let's go on and see another scenario to balance our rep black tree. As a new key value, let's insert key value of 62 this time. We initialize its node constructor values as usual. We create a Y node to update the parent nodes of node 62 and X node to find its insert location in our rep tree. We iterate through the while loop until we move X to insert location and Y to its parent. At line number 22, we point insert node's parent to Y, means node 62's parent becomes node 50. At line number 28, we do actual insertion of node 62 at the right pointer of Y node. We skip next two if statements as we are not at the root node and the node inserted is not the second node after the root node. So again, we get to balance method to reform our rep black tree after our new inserted node with key value of 62. At the balancing section, we get our newly inserted node as input argument of Z, and we create uncle node, which will help us to determine with what type of scenario we are dealing with at the incoming steps. At line number 3, we go through our while loop as we have a red parent for our Z input. At line number 4, we check whether the reformation will be at the left subtree or at the right subtree of our rep black tree. So if Z's parent is equal to Z's grandparent's right pointer, reformation will be performed at the right subtree, else it will be at the left subtree. So yeah, when we look at our visualization, we can see that Z's parent is equal to Z's grandparent, and this means we will execute the if statement at line number 4. At the next line, we know that uncle node is equal to Z's grandparent's right or left subtree depending on the subtree that we are applying reformation. In our case, it is Z's grandparent's left pointer. At line number 6, you can see at the left corner our rep black tree scenario number 2 describes that if Z's uncle is red, then we recolor. So starting from line number 8, we recolor uncle node back to black, Z's parent node to black, and Z's grandparent to red. At line number 11, we change our Z value to Z's grandparent. By doing this, we ensure that operation of scenario 2 was performed for all corresponding nodes such as uncle node, parent node, and grandparent node. So we know that at the next iteration, we will not be touching any of these nodes again. After executing this if statement, we are at the next if statement now where we check if Z is equal to root. Because if we had more nodes in our rep black tree, then we would go through the loop and continue reformation of our rep black tree depending on the scenario. But in our case, we testify scenario number 1, where Z is root. So we break the while loop and color our Z, which is our root node. To see our last scenario, we continue insertion by adding key value of 55 in our rep black tree. So I will slowly step up through our code example and start explaining when we are doing reformation of our rep black tree. So again, we assign our Z value as our last inserted node with key value of 55. Unbalancing occurs at the right subtree because Z's parent is equal to Z's grandparent's right pointer, and that's why our uncle node will be equal to Z's grandparent's left pointer. Next, we check our scenario number 2 if Z's uncle is red. It isn't so, we skip to the else statement. After else statement, we check whether we have scenario number 3. Yes, we do because Z is equal to Z's parent left pointer. And when we look at scenario number 3 at the left bottom corner, we know that we should rotate Z's parent. To do this, we first assign Z to Z's parent and apply right rotation. As an input argument, we assign our Z node to be our X input, since it will be the node to be rotated now. At the next line of code, we basically show where our Y node will be. Before going into next line, I would like to remind you that our Z node is now called as our X node because of the naming at the input argument of method right rotate. So when I say X node, you know that it is our Z node. Okay, so next, X.left becomes Y.right. Nothing special here, it's just the way how right rotation is applied. I am assuming that you remember this from definition of AVL tree or insertion of AVL tree lectures. If you haven't watched them yet, I highly recommend watching it before you jump into red black tree lectures, because there I explain rotations more in depth, where now we are actually applying the same methodology. So yeah, at the next line we basically check if node y's right pointer has a data element or key value with the node, because if it did, then we needed to update its parent since it would point to x after rotations are applied at the upcoming steps. So it doesn't, and we skip the if statement and get to the line where we basically update the y parent. Y parent now will be x's parent because again, at the upcoming steps, y will be taking the place of our z node and z node will be going to be child of our y node. After parent update, we have an if statement. I assume it's very easy to understand just by looking at the statement why we have it. We have it because after rotation, if parent is null, then we know that the rotated node will surely be our root node. But this is not the case here, because our z has parent node. Then we skip this statement. At the next two statements, we basically check whether we are rotating our node from right to left or left to right. So if x, or in other terms our z node, is equal to its parent's right pointer, then we know that we will rotate our z to right, else we will rotate it to the left. In this case, we will rotate to right. So we update x parent's right pointer to y, and y's right pointer to our x, which means our z node. At last line of right rotate method, we update x parent to y because now its parent is y. So we finished with scenario number 3, but we still have one more step to go, because at this current state we also testify scenario number 4. Now our z's uncle is black and we have right case which requires left rotation. As we remember, scenario number 4 requires rotation of z's parent and we recolor. As I have mentioned before, we change the order of execution in this approach, so we first recolor and then do rotation. So at the next line, z's parent becomes black and grandparent red. In left rotate method, this time we take z's grandparent as our input x argument and perform rotation. So our x will be 50 this time, y will be pointing x's right. X's right pointer becomes y's left pointer. We skip the first if statement because we have t null at the left pointer of y. After if statement, we update y's parent because at the coming steps, node y will go up and node x will go down left. X parent is not null, so y cannot be our root. At the next line, we skip else if statement because we are forming right subtree. So the next else statement will be executed. X's parent's right pointer becomes node y, and node y's left pointer becomes x. And we update x's new parent because its parent is not the node with key value of 39, but it is node y with the key value of 55. After rotation complete, we check if z is our root. It is not, so we repeat the while loop. At this current state, while loop will check if we still violate red black tree definition. We don't, because z's parent color is no longer red. So we skip while loop, and at line number 48, we are being sure that our red black tree has black root. In this lecture, we learned how red black tree insert operation works using some practical examples. In the next lecture, we will see how delete operation works in red black tree. I hope you enjoyed this lecture and hope to see you in the next one.